I would like to welcome you to this afternoon session on AI in security, a potential to make and break a secure connected world. The tutorial is going to be delivered by Professor Debdeep Mukhopadhyay. I am extending a hearty welcome to Professor Mukhopadhyay to this session. I will just introduce his profile briefly. Professor Debdeep Mukhopadhyay is currently a professor at the Department of Computer Science and Engineering, IIT Kharagpur, India. At IIT Kharagpur, he initiated the Secured Embedded Architecture Laboratory, SEAL, with a focus on hardware security. He has worked as visiting scientist at NTU Singapore, visiting associate professor of NYU Shanghai, assistant professor at IIT Madras, and visiting researcher at NYU Tandon School of Engineering, USA. He holds a PhD, MS, and BTech degree from IIT Kharagpur. His books include Fault-Tolerant Architectures for Cryptography, Hardware Security by Springer, Cryptography and Network Security, McGraw-Hill, Hardware Security, Design, Threats and Safeguards, CRC Press, and Timing Channels in Cryptography, Springer. He has written more than 250 papers in peer-reviewed conferences and journals and collaborated with various Indian and foreign organizations. He has been on the program committee and editorial boards of several top international conferences and journals. Professor Mukhopadhyay is the recipient of the prestigious Shanti Swarup Bhatnagar Award of 2021 for Science and Technology and is a fellow of the Indian National Academy of Engineers. He was awarded the DST Swarna Jayanti Fellowship in 2015-16, Data Security Council of India Award for Cyber Security Education, ASEM Duo Fellowship, INSA Young Scientist Award, INAE Young Engineer Award, Associateship for the Indian Academy of Sciences. He was awarded the Outstanding Young Faculty Fellowship from IIT Kharagpur and the Techno Inventor Best PhD Award from the Indian Semiconductor Association. He has recently incubated a startup on hardware security, ESP Private Limited at IIT Kharagpur, and is a senior member of IEEE and ACM. Dr. Mannar Alam is currently a postdoctoral associate at the Modern Microprocessors Architecture Laboratory, Center for Cybersecurity Research Institute, NYU Abu Dhabi in the UAE. Mannar holds a PhD degree in Computer Science and Engineering from IIT Kharagpur, India. He received the prestigious IBM PhD Fellowship Award during his PhD. He also holds an MTech degree from IIT Dhanbad, India, and a BTech degree from IEM Kolkata, India. He worked as a visiting research assistant at NTU Singapore. So, Professor Mukhopadhyay, again, welcome to you and Dr. Alam, and over to you.
Welcome to our tutorial at the VLSI Design 2022 conference. The title of our talk is Artificial Intelligence in Security, Potential to Make and Break a Secure Connected World. The tutorial will be delivered by myself, Debdeep Mukhopadhyay. I'm working as a professor at the Secured Embedded Architecture Laboratory in the Department of Computer Science and Engineering at IIT Kharagpur. The tutorial will also be co-presented by Mannar Alam, who is my former PhD student from SEAL Lab, and presently he is a postdoctoral associate at New York University, Abu Dhabi. So a brief introduction of ourselves. So we essentially are a team which we called as the Secured Embedded Architecture Lab, or SEAL. We have been working from around 2008 at IIT Kharagpur, India, primarily on in the area of hardware security, looking into various attacks and countermeasures. Recently, we are also working in the confluence of machine learning and security, and that motivates us for this tutorial. So we all know that we are in a connected world. We are all distantly located, but still connected to each other. And therefore, we have to we must ponder that when we are communicating, there are several embedded devices, processors, sensors, communication hardware, which are continuously collecting, sending, and acting on various kinds of data, which is often of critical nature. And therefore, while this connected ecosystem can revolutionize the quality of modern day life, but it is also equally important to keep security in perspective. And therefore, there is continuous handling of very critical information, which needs to ensure integrity and privacy of data. And that obviates the necessity of the usage of encryption operations. Likewise, When we are talking about Internet of Things and connected world, we essentially envisage billions of devices communicating with each other. And therefore, in order to build such a heterogeneous network in a resource constrained environment, we need suitable hardware roots of trust. And in this context, we come across very promising hardware security primitives like physically unclonable functions or PUFs. However, one may ponder that whether security is a real reason of concern. And when we look at the news recently, we see often various, like attacks on IoT systems, on cyber physical systems. We see the advent of side channel attacks, power attacks, fault attacks, often crippling various hardware and commonly known computing systems. For example, recently there were news about Plunderbolt, which essentially is a mechanism to perform fault attacks on the popular Intel SGX platforms. So therefore, it's a real reason of concern. Security is not only nowadays in the domain of the academic world, but it is also equally important in industry. And therefore, we try to look at the prevalent threats on the connected world. And while we know that mathematically strong crypto algorithms are a good beginning and an important one, but they are not enough. And therefore, we need to look at the implementation level threats, which targets insecure implementation of mathematically secure crypto algorithms. Likewise, the roots of trust, like physically unclonable functions, which promises to be physically unclonable, are often challenged by modeling attacks or machine learning attacks, which tries to develop mathematical models of such kind of constructions and therefore completely jeopardize the promise of on hardware security that they provide. On the other hand, we are continuously threatened by various crypto viruses like malwares, ransomwares, and therefore it is equally important to look at these threats and try to understand how we can develop suitable safeguards against such kind of attack vectors. And therefore, the natural question is, what has got machine learning or deep learning or essentially artificial intelligence in general has to do with such kind of threats? Are they really a boon or bane? It turns out that essentially AI or machine learning can be used for both purposes. It can be really used to unearth more devastating implementation level attacks, try to pose threats on hardware roots of trust. On the other hand, it can also be used as a great detection framework, or through which you can obtain early safeguards to develop suitable protections. So this motivates us to this tutorial, which tries to answer this question and address whether artificial intelligence in the context of hardware security in particular is a boon or bane. So we first of all try to address AI for attacks, wherein we try to show how deep learning or machine learning essentially have been used to attack crypto algorithms using what we call as side channel information, which are more powerful and more efficient than standard statistical based techniques. We show how this power can be utilized to unearth even masking based protections. Likewise, we also take a look at fault attacks, wherein the faulty computations in crypto algorithms are utilized to perform attacks. So we show how machine learning can be used as a mechanism to develop or to understand the threats of such kind of fault injections, and therein it can be used for both purposes. It can be used to develop and mount efficient fault attacks, and on the other hand, it can also be used as a detection framework to test your countermeasures and detect leakages because of these attack vectors. Likewise, we also discuss about how machine learning can be utilized to generate efficient approximate models of PUFs, and at the same time, how one can develop CAD frameworks to test such kind of hardware security primitives. We also try to look at AI for defenses. In particular, we try to take the case study of ransomwares, which we are know as growingly menacing malwares, which basically tries to encrypt our file systems. Now, in the process of doing that, it often leaves very distinct footprints on the hardware performance monitors on our computing systems, which can be caught by your advanced machine learning techniques. Likewise, we also try to look at another side channel attack vector, which are called as rowhammers, which tries to exploit the fault tolerant aspects on the DRAM chips And using that, it tries to develop a fault injection mechanism. So in our study, we try to look at how machine learning can be applied to analyze such complex memory access patterns and create early detections or alarms for rowhammer-based attacks. So this is a rough outline of our talk. I will be trying to talk about part 1, which is on AI for attacks, whereas Manar will be covering on AI for defenses. So with this, we start the first part, which is on AI for attacks. And in particular, we start with side channel attacks. So what are side channels? So side channels are basically covert channels that leak information which the designers of the crypto algorithms did not consider. So when there is a crypto algorithm, which will be a very mathematically strong cipher, and you are implementing them on the real device, whether it's a software device or an embedded device or a purely hardware device, it often leaves footprints on time computations, the heat dissipations, the current, the electromagnetic radiations, the behavior under faults, which can be observed by an astute observer. So the attacker in this case tries to not only monitor the inputs and outputs, which you often call as the plain text and the ciphertext of the encryption algorithm, but at the same time, it also tries to acquire traces, which are, for example, maybe the current consumption of the device. Now, it's quite magical to kind of observe that one can perform statistical analysis to retrieve the complete secret key bits of even well-known and standard ciphering algorithm. However, in order to do such kind of experiments, you need a proper experimental setup. And here is some a quick look into the experimental setup for doing side channel attacks at our institute. So what we try to do is, for example, we take a device under test and we have a current probe, and this can be replaced by other probes for other attack vectors. And we try to monitor the power consumption in an oscilloscope. Now, while we do that, we also observe the inputs and the outputs by a PC, which tries to do the synchronizations of the input, output, and also the accompanying trace information. So therefore, later on, we try to take these traces and perform statistical analysis on them to retrieve the secret key. So now the question is, what kind of methods do we have for side channel analysis? It turns out that there are two distinct methods of doing side channel analysis. The first one is what are called as profiled analysis, while the other one is called as non-profiled analysis. So in profiled analysis, which are the strongest forms of side channel attacks, we require the adversary to have access to an identical experimental device that he can program based upon its requirements. So for example, one can take the profiled attack, the profiled device, and set the key or the secret key to different values and observe the corresponding power traces, for example. So during this phase, it tries to do a profiling. So it basically tries to categorize or tries to categorize the power traces depending upon the secret key values. Now, I would like to mention here that all these attacks are based on divide and conquer, which means when you are targeting ciphers like AES, for example, like Advanced Encryption Standard, which is the de facto worldwide standard for block ciphers, you usually deal with key sizes of bigger than 128 bits. And therefore, one cannot do an exhaustive search of 2 to the power of 128. However, these attacks are based on divide and conquer, which means typically, say, for a 128-bit key, you try to decompose it into 16 bytes and you try to recover the key byte by byte. So we basically guess each byte, and each byte can take 0 to 255, that is 256 possible values. So therefore, what you do is you take these power traces and you try to categorize these power traces in the profiling phase based on the values that these key bytes can take. Now, when you are going for the attack phase, where you essentially have got a target device, the objective is that you should be able to obtain the secret key. Note that during the target phase, you do not have any control about the secret key, but you should be able to recover the key with as minimal observations as possible, because you are expected to have minimum exposure or availability of the target device. On the other hand, in the non-profiled analysis, you do not have any availability of the profile device. So in this case, what you try to do, you try to target an intermediate computation of the device, and then you try to basically obtain the secret key by applying some kind of statistical techniques. So usually what is done is you try to do an intermediate computation of your ciphering algorithm, and then you try to apply some kind of power model. So these power models are usually dictated by the VLSI theory. For instance, it could be as simple as a Hamming weight power model. And then you try to kind of develop a hypothetical power trace based upon the secret key guess that you do. And note that the secret key guess you are doing in a byte by byte fashion, which means you are again adopting a divide and conquer strategy. And therefore, depending upon the key byte, you will have different hypothetical power traces. Now, remember that you are also observing the actual power trace as an attacker. So what you try to do now is you try to correlate the power traces that you have observed, which are the real power traces, with your hypothetical power traces. Now, if you have got a strong correlation, then there is a very strong likelihood that the key that you have guessed or the key byte that you have guessed is correct. You repeat this process for all the key bytes, and therefore you can recover them quite easily. So, so now the question is, right, how can we apply deep learning method for, say, profiling based side channels? So this was probably one of the first works which was published by Maghrebi et al. At Space 2016, which is an international conference on hardware security and crypto engineering that we do annually in India. So in this case, we try to kind of apply deep learning based approach to see that side channel attacks can work quite nicely. So what is done over here is, as shown in the illustration, you have got a target device, and remember that this is the profiling phase, so you have got full control on the key. So you change the key byte maybe for 0 to 155. So you basically change them for all the 256 values, and then you essentially perform the encryptions. Remember that you are observing the power traces in a signal acquisition step, and in this process you try to train CNN architecture based upon based upon the power traces that you're observing. So the power traces are essentially are being fed as an input to this architecture, and you are performing training by labeling the power traces based upon the key byte value. Okay, so remember the key byte value can take, say, 0 to 155 values. So you effectively spread out the or label the keys or label the power traces into different key byte values, okay, in the profiling phase. So now it turns out that when you are going into the attack phase, remember that during the attack phase you do not have control on the key, and therefore during the attack phase, when you have again performed some amount of signal acquisition, you go into the classification stage. That means you basically feed the the power trace as an input to your classifier, and the classifier should essentially give you probabilities among the various 256 key bytes that are possible. So you try to repeat this for various a large number or a sufficient number of power traces, and then the idea is that you basically try to return the maximum the key byte which has got the maximum probability as per as your prediction using the DNN is concerned. Okay, so therefore, right, using this technique you are essentially able to obtain the secret key, and it turns out that this is a very powerful method. And if you compare it with your traditional statistical based techniques which are often adopted, which have been applied previously for profiling attacks, which are called as template attacks. Now when you apply template attacks, you try to make some assumptions. The assumption is that the leakage distribution has a Gaussian pattern, okay, Gaussian distribution. However, when you are applying deep learning, it turns out you can relax such kind of assumptions. Moreover, in traditional template-based profiling attacks, you also need to do a bit of pre-processing. For example, often it may happen that the power traces, they get desynchronized, and therefore you have to synchronize them. Likewise, you may need to apply some kind of denoising techniques. However, deep learning, because of its power, it can completely kind of relax these such kind of requirements, and therefore can give us more efficient attack methodologies. Likewise, there is another very strong advantage of applying deep learning for profiling based side channels, which is on attacking countermeasures. Now, one of the very popular countermeasure against classical statistical based side channel attacks is by using masking. So in masking, what you do is basically you try to randomize the computation. So imagine that there is an input intermediate data, say X, and you want to kind of randomize that to ensure that the power consumption does not depend upon X. So what you do is you randomly generate a mask, say call it as M, and you do a computation on M. In another instance, you do a computation on X XOR M. So you try to kind of mask the value of X using the random value M. However, deep learning, because of its ability to combine multiple leakage points, works quite efficiently and still are able to circumvent such kind of protections. So then the next natural question is, can we apply deep learning for non-profile based attacks? So in this very nice paper in Teachers 2019, Benjamin Timon shows that you can still perform such kind of non-profile based learning. So what you do in this case is, remember that in this case you don't have a profiling phase, so you don't have any profile device on which you can set the key to any choice or any value of your choice. So rather, the idea that is exploited is quite interesting. So what you try to do is you try to again guess the key byte. Remember, you have got no control on the key byte, but you try to guess the key. And then you try to go ahead with by XORing the plain text. So this particular computation shows you maybe the first round of any standard block cipher where you XOR the key with the plain text and you apply a nonlinear transformation which is called as S-box. So now what you do is you basically guess this key byte, you XOR it with the plain text. Remember, you have knowledge about the plain text, and you perform this intermediate computation, and then you come to this target step. Okay. And now in this target step, you essentially try to, depending upon its corresponding value, you try to basically see that, you try to train the power traces that you're observing, and using that power trace, you try to essentially, train a model or a machine learning architecture. So what you do is you basically train it based upon the value of this intermediate computation. Now note that this intermediate computation, if you are observing, again, you're applying if you're observing a byte, for example, so this is a byte by byte transformation, you try to, so this byte can take 0 to 255 possible values. So therefore, what you try to do is you try to train your model based upon the output value of this S-box. Okay. So now this, so therefore the idea is that if your key guess is wrong, okay, that is, if you have guessed your key guess wrongly, then you should not be able to, train the machine learning efficiently, and therefore you will find that your training accuracy will be pretty poor. On the other hand, if you have guessed it correctly, then your training accuracy will be high, as you can observe by the reduction of the loss of your training, and eventually, right, when you get a get a good training, then you can pretty much be sure that the key that you have guessed during that training process is a possible candidate key. Okay, and that way you can distinguish the correct key from the wrong keys. So the idea here is that you can perform the deep learning based attack. Again, this is a very powerful form of attack, and in the paper they have various other techniques like sensitivity analysis to unearth the points of interest, through which they show how you can subvert countermeasures like masking without the knowledge of even the order of the masking. For example, the masking can be of different orders. It can be first, typically if you have got like one mask, then we call that as first order masking. If you have got two mask values, then you call that second order masking. And traditionally people have shown that when you're increasing the order, then it becomes more and more difficult to perform these attacks. However, deep learning seems to be quite powerful and work even without the knowledge of the order of masking, which is, I think, a very strong selling point of deep learning for performing non-profiled or in general side channel attacks. So the other question that we address, and maybe it should be mentioned here at this point, is in the context of cross-device side channel attacks. So as I mentioned, that when you are talking about template-based attacks, you have got access to the dummy devices, and using them, you essentially train a machine learning model. But then when you go in to perform the actual attack phase, then you need to perform your attack on the original, or your device should be again the same device. That means your target device should be similar to that of your dummy device. However, if you are trying to kind of perform your attack on a different device, then it can be pretty much challenging because of the influence of temperature, noise, and other external uncontrollable parameters. Your model, which you have trained on the dummy device, on a different device, it may not accurately work. Okay, and this poses us several challenges. That means you need to again train your device on every new target device, and that means that it becomes pretty cumbersome. So this is exactly shown over here. That means if you are training on different device, and if you are going to attack a different perform your attack on a different device, or your target device is quite distinct from your dummy device, even if you are targeting the same crypto algorithm, your models will not work accurately. So you need training for new dummy target devices again and again. So what we try to do is, in order to avoid the requirement of this huge amount of time of retraining, we try to see whether you can still perform using the techniques of machine learning in less amount of time. So in particular, here we try to adopt the transfer learning strategy. So in traditional machine learning, we know that if you have got a data set and a machine learning model 1 and a data set 2 and a machine learning model 2, these are pretty distinct processes. However, in the context of transfer learning, we try to apply your knowledge in like training the first data training based on the first data set, and you try to kind of transfer that knowledge on a different data set and a different model. So that we try to kind of alleviate the requirement of like needing to rebuild the model from scratch every time, and try to use the previous knowledge for a similar task to be performed. So in this case, remember, when you are trying to perform this attack on a different device, you essentially have the same task, only that the features of the power profiles are probably different. For example, you may have a different noise level in a different device, you may have a different point of interest. So the question is, can you apply transfer learning to learn these new features without a retraining process? So what we try to do in this work, which we published in ISQD in 2021, is try to have a one-time profiling where you essentially like apply a lot of effort to train on a given device. So you have got a large profiling data, and then you try to, for a target device, to fine-tune your model. So here we try to apply like transfer learning strategy, and finally, once you have developed this fine-tuned model, you try to apply and attack the corresponding target. So in particular, let us try to talk about this fine-tuning process. So in the fine-tuning process, we take our our neural network and try to kind of like train it in an intelligent manner using these techniques of transfer learning. So what we try to do is, rather than allowing all the layers to be like trained, that means all the weights of all the layers to be like updated by during the process of of back propagation and update it continuously. What we try to do is we basically try to update only the initial layers, okay, which we fine tune, whereas the last few layers are frozen. So what we mean is by frozen is that these weights are not allowed to be changed during the back propagation process. So why do we do that? Because the last few layers are often essentially catered to the specific task at hand. And as I said, that in our particular scenario or the problem scenario, our task is still the same, right? Because you are still performing like a profile attack, and therefore the prediction function that you essentially have, or the predictive function that you need in language of transfer learning, remains the same. Okay, but what really changes are the features, and it turns out that the initial layers are more important in terms of learning the features, and therefore we essentially perform like fine tuning of the weights of the initial layer. So this technique helps us to perform this fine tuning process with less number of observations, giving us lesser like time requirement for the overall attack. So here are some results on unprotected implementation. First of all, to motivate. So here we see that we have a base model which is being profiled with T1, and when you want to attack a different device, then your attack doesn't work. Similarly, for when you want to work on attack with T3, again your attack does not work. So this is quite expected. However, using our technique, when you have a base model which is profiled with T1 and you fine tune your model with T2, and likewise you fine tune your model with T3, and you perform the attack with T2 and T3, in both cases we are successful. So this plot shows you the rank of the correct key byte with the number of tests, that is observations, and you see that the rank of the correct key falls quite fast, and therefore with less number of observations you essentially are able to ascertain the correct secret key byte. So the attack is successful with small number of observations. So here are more details of the experiment. So we take 3 devices, T1, T2, and T3, which essentially have got different noise levels and different points of interest. Points of interest means when the time instance when your secret key comes into execution. So you can see here that in a standard deep learning, probably you will require 5,000 traces, and for T2 device you will require 1,000 traces, and for T3 you may require 15,000 traces. The reason being is that the standard deviation of noise is pretty high in the device T3 compared to the other devices. So now in our case, what we have done is we have essentially say what we want to kind of highlight is we essentially want to perform. Of course, we can suppose we have got a model that we have trained with T1, and then you want to perform your attack with T2. So in a standard case, you again need to kind of retrain the model for T2. But in our case, what we can do is you can probably like develop a model. Say what you can do is, if you want to apply our technique, which we called as trans SCA, then you can essentially have a model which you have trained for T2, and then you can refine your model for T1 and then perform your attack on the device T1. So if you see the results here, you can observe that in a standard, like deep learning based SCA, probably for the device 1, you are requiring 350 power traces. But if you observe that you need, like when you want to kind of, like extrapolate the trans SCA from the model that you have built for T2, then you need only 250 observations. Okay. Whereas if you need to kind of, like update the model from T3 and do a trans SCA from T3, then you just need 300 power traces. More interestingly, you can see for the device T3, where there is higher noise, you can see that you can perform the trans SCA from T1 using only 750 observations, and likewise from T2 with only 925 observations. Okay, so the initial fine tuning, that means the number of traces to fine tune are shown here as 1,000 and 6,000, and you can see that that is pretty less than 15,000, which you are probably required if you had, again, needed to train the model for T3 independently. So this shows that the overall, reduction in the number of observations, and likewise the improvement in terms of the efficiency of the overall attack. So we also have different, like some other techniques that we propose in the paper. In particular, we kind of extrapolate the idea of sensitivity analysis to show that how our to kind of demonstrate how our refining of the model works pretty accurately. So sensitivity analysis, as we know, is a mechanism, or is a method that we adopt in machine learning, trying to kind of understand the importance of the input features in terms of the overall accuracy. So now, if you observe, for example, let's see the top graph over here, you can see that there are 3 colors showing, the different profilings that have been done in context to the device T1, T2, and T3. So in particular, if you observe the blue line, this is the base model that has been profiled for the device T1. And now when you want to kind of refine or fine tune your model for T2, then you can observe an interesting fact using sensitivity analysis. So I would like to mention here that the point of interest, that means when the secret key gets involved, is at around about the time instance 15 for the device T1, whereas it is for the device T2, it is somewhere around the time instance 10. So when you are refining your model from T1 to T2, your refined model should be able to understand that. And it turns out that the sensitivity analysis shows a peak at T1 for the at around 10 for the refined model, which is fine-tuned with T2, showing that it is really able to learn that feature effectively. Interestingly, you will find that the peak at the time instance 15 dips, showing that there is a reminiscence of the old model. And likewise, the same thing you can observe for, like when you are taking the model or the base model at T1 and retraining it or fine-tuning it for T3. So this can be observed, you can observe this phenomenon for the other cases as well. So, therefore, I mean, here is a quick overview on the results of protected implementations or masking. So we show here 2 devices, T1 and T2, on which masking has been implemented. And you can observe that there is a device T2 for which a profiling probably would require as many as 1 lakh observations, but that is 10 to the power of 5 observations. But you can apply trans SCA, and what you can do, therefore, you can train on T1M, and typically T1M will require say 10,000 power traces to be trained. And then if you apply trans SCA, it will take you around 200 power traces. Okay, so that means you can do your attack with quite a less number of observations, because like you essentially would require probably 30,000 power traces here, and then like the final attack will take you around 200 power traces. Overall, it is much lesser than 10 to the power of 5 observations. Okay, so this shows the efficacy of applying transfer learning to therefore develop a base model, fine-tune the base model for another device, and then perform the profile attack. So overall, there is a significant reduction in the number of traces, and the advantage is even more when there is a more noisy scenario. So this brings me to the second part of my talk, which is in the context of fault attacks. So here is a very simple interpretation of fault attack. So there are 2 devices which are identical weights and of course cost. So now if I essentially make two packages like 25 object 1 and 10 object 2, and likewise 10 object 1 and 25 object 2, then these two scenarios are distinguishable, are not distinguishable or indistinguishable. So if there is a like a parcel who is observing, like who is a curious person who is observing the weight and the price, will not be able to distinguish between these two scenarios. However, if you apply a fault attack or a fault injection so that you break exactly one object, then you can see that the refund that you will probably be claiming will be different in both the scenarios, helping you to distinguish between these two contexts, okay, or scenarios. So the question is, does this attack or this leakage, right, does it also extrapolate to cryptographic instances? So here we show that it really does. So for example, if you take a secret key algorithm and suppose you have got a key 1 and key 2, these are two different embedded environments. You have a correct execution, then both of them are indistinguishable. But it turns out if you have a faulty execution, then they are distinguishable, which leads to a leakage. So people have shown that these fault attacks essentially are quite catastrophic, and leads to the leakage of the secret values. So in the context of block ciphers, we talk quickly about AES 128, so which is the de facto worldwide standard. So in one of our previous works in 2011, we showed that a single fault is enough to compromise the secret key of AES by reducing it to a paltry 256 values. If you get a double shot, then you can uniquely retrieve the key. And nowadays, there are a plethora of fault injection techniques which have been developed based on low-cost techniques like clock glitches, voltage glitches, and also more sophisticated techniques like laser guns and electromagnetic radiations. People have shown that you can also perform these fault injections using software mechanisms like rowhammer, which are bugs in the DRAM chip. And likewise, people have like one of the recent fault attacks, which are called as plunderbolt, tries to handle, tinker with the voltage frequency scaling of Intel SGX platforms and shows how one can secret RSA and AES keys. So let us take a quick look at why fault attacks work in the context of AES. So here is a typical state of the block cipher AES, where there is a single fault that has been created. And remember that at this point, the attacker has no control on the value of the fault. So the fault is kind of arbitrary. But when the fault propagates through the block cipher, then because of the transformations that we have in the block cipher, it leaves distinct patterns. As you can observe here, that there are some bytes which are equal, there are some faulty bytes which are double the other, and so on. So now what the attacker does, it tries to kind of guess parts of the key. It tries to kind of go back and tries to exploit these interrelationships to develop efficient attacks. So as I said, that a single fault is enough in the context of AES 128 to reduce the key size of AES key from 128 bits, that is 2 to the power of 128 values, to only 256 possible values. So this leads us to different fault analysis methods. The technique that I mentioned is usually called as differential fault analysis, or DFA, where the attacker has got exposure to the ciphertext and the faulty ciphertext, that is the correct ciphertext and the faulty ciphertext, and then follows it up with this analysis to get the secret key. Now, there are some recent attacks which are called as statistical fault attacks, where the attacker probably has access to the only ciphertext and uses that to get the secret key. There are some recent improvements of these techniques which are called as statistical ineffective fault analysis, or CIFA, and fault template attacks, which essentially have been shown to be even more powerful to also break countermeasures. So talking about countermeasures, usually the technique that people had adopted was classical fault tolerance. So you try to kind of have various kinds of redundancies, like in the time domain, space domain, information domain, and using that, you try to develop various protections against fault attacks. Likewise, there is, like the detection-based techniques, there are also techniques which are called as infection type, where there are no explicit detection steps, but rather internally inside the ciphering algorithm, or the ciphering algorithm along with the countermeasure, it tries to disturb the information in the faulty state, so that even if the attacker has exposure to the fault value, it is not able to correlate that with the secret key. So interestingly, there was an infective countermeasure which was proposed in FDTC 2012, which was subsequently also broken. So I will talk about that in the context of our deep learning based experiments. So therefore, the big question is, if I have got a block cipher along with countermeasures, how really can I test them? Because I would like to mention here that the fault attacks really have become more and more powerful, and therefore it can really break with as minimal number of fault instances as possible. So for example, in AES 128, you just need a single fault to compromise. And therefore the question is, right, how really can you really analyze your designs? Okay, and it is not really good probably to to say that it is not the problem of the designer of the crypto algorithm or the implementer. Rather, I think it's a proper handshake through which we can develop protections against such kind of attack vectors. So the question is, right, how do you know that what is secure and what is not? Because the big challenge is that you may have different kind of countermeasures with lot of internal details, and likewise the fault injection techniques are also continuously evolving. So is there a holy grail method through which you can understand fundamentally the leakage because of such fault instances? So this motivated us to look into automated leakage assessment, wherein we try to kind of model the leakage because of faults more fundamentally. In particular, all these fault attacks are based on what are called as differential analysis on the ciphertext. So we try to relate the delta C, which is the differential on the ciphertext, with the plaintext and the key, and also with the fault value. Now the fault value can be the value that you're inducing because of a specific fault model. So it can be a byte fault, bit fault, or like a random fault, and so on, like maybe a stacked fault. But however, right, what we want rather is to capture the leakage because of this interrelationship. Now, how do we capture leakage? So, I would also like to mention that probably like one may wonder that the secret key is important, but it turns out that the fault is equally important. So what I mean by that is that the value of the fault that you're inducing, if the attacker is able to ascertain the value of the fault, then that also can help to significantly reduce the entropy of the secret key and has an equivalent effect in terms of the leaking the key. So therefore, both fault and key are treated as secrets in this analysis. So this leads us to this information theoretic framework, where we try to kind of capture the mutual information on the delta or the differential on the ciphertext with both the fault and the secret key, given the distribution on the plaintext, because the attacker has control on the input plaintext. And then the big question is, how do you really detect leakage? So in this case, we try to apply the theory of non-interference. So what is the theory of non-interference? So the theory of non-interference is a very popular technique which is often used for probabilistic program checking, and we try to borrow these ideas in the context of fault analysis. So in this case, or in this type of analysis, you try to differentiating on the variables. For example, you may have random variables which are associated with secret data, which we essentially set a value high, and likewise you may have some public information which we set a value low. So now what we try to do is we essentially try to kind of simulate your device, which essentially has got the ciphering algorithm and the countermeasure, by setting different public values, but by essentially feeding in different public values. But what is most important is that we try to give different values of the secret. So now what we try to do is we try to observe the output and see whether the output distribution varies depending upon the value that you are setting in the input, in terms of, the secret value that you are setting at the input. So if you observe this illustration, you can see that this is in the first simulation, we essentially set a value high with H. In the second instance, we set it to H dash, and then try to see that whether the output observable O and O dash are distinguishable. If they are distinguishable, then that implies that the output essentially is leaking information about the secret. Now, this is a pretty easy to verify mechanism, and you can use statistical techniques to detect and analyze such kind of leakages. So in our paper in DAC 2019, we try to develop a framework using statistical t-test, which is the hypothesis testing framework, and try to see that whether, like when you're doing fault simulation, whether you can detect such kind of leakages and you can predict the fault attack vectors. So now the question is, right, why do you want to really improve by applying deep learning? Now there are some issues with our statistical hypothesis test based methods, but first they are suboptimal, and secondly they also give false negatives, and moreover they are only capable of detecting the first order moments, and largely, right, they are not being easily extendable to higher order higher order analysis. And in particular, when we talk about countermeasures like masking, often we need to deal with higher orders, and therefore, right, it is important to be able to be scaling to higher order instances. So this brings us the deep learning, because deep learning in general is a very powerful method and a powerful tool, and its capability to learn multivariate scenarios and the complex interrelationships among the various features that are that we need to analyze in this context helps us to come up with a a better framework compared to our initial framework using LFA. So in particular, I would like to kind of quickly show an illustration that we use to kind of define the overall framework using deep learning. So what we do is we take a crypto device and we basically simulate it with different fault instances shown here as F0 and F1, and then you get two different classes of faulty ciphertexts, and then you try to train a machine learning architecture by applying various techniques like k-fold cross validations to ensure that there are no really memorizing the input data and overfitting and so on. And the idea is that if the machine learning is able to be trained, then you should get a validation accuracy should be just deviant from 0.5, because 0.5 would be the the probability of guessing and differentiating between these two classes in the random instance. But if the machine learning tool is able to learn this pattern and able to distinguish between these two scenarios significantly, then potentially there is a leakage. So what we try to do is, in this analysis, we try to observe the output vector in all these instances, and try to see that if this distribution that you are observing here is significantly deviant from the 0.5 value. So in this, again, we apply statistical hypothesis testing and we develop the corresponding thresholds using such kind of theory. So overall, of course, there are more details in terms of how do you simulate them based on various fault models, which I would like to skip for the sake of time. But rather, it would be probably interesting to show the results. So in this case, we talked about the infective countermeasure, remember? So here we apply our deep learning based method and see whether we can unearth the the attack. So it turns out that our framework is able to detect the leakage quite easily. And interestingly, the initial technique using LFA is not able to open, and this shows that there are some false negatives. But our deep learning based framework is able to detect these leakages, and therefore can give better guarantees. Likewise, we also investigated another countermeasure which is called as bane, which we show here, which was published in IEEE TIFFs in 2016, and we show that our framework is able to detect attack vectors against such kind of countermeasures as well, and break these countermeasures. So therefore, it is a very powerful tool. So likewise, we continue various kinds of explorations, detection-based countermeasures. We also try to show how statistical-based techniques, which are called as CIFA, are sound. So in particular, we try to look at the present-day CIFA countermeasures, which was published recently in IEEE TIFFs 2019, and also another work which is called as impeccable circuits 2, and we show that they are essentially sound against fault attacks, showing that the theory that was proposed in the paper are essentially still standing sound. Another advantage of applying deep learning was, as I said, in the context of understanding the leakage order. So in particular, in fault attacks, you need to deal with higher order analysis. So what I mean by higher order analysis is that the fault, essentially, when it is propagating through the cipher, it can leave its footprints at different bytes. And often an analysis may require to kind of account for multiple bytes simultaneously, and the number of bytes that you need to kind of deal with decides the order of your analysis. So what we try to do is we try to apply sensitivity based analysis, and using that we try to automatically understand the leakage order. Therefore the evaluator need not give the leakage order to the tool, but rather the tool is smart enough to learn the suitable amount of the order that it needs to tackle. So here is an experiment to show that, in particular in the context of infective countermeasure, I will show you that these are analysis that we use and we apply the sensitivity analysis to detect the order. So to observe that what we do is we start initially with a 4 order. So we have seen that our attack initially works with a higher order evaluation, and then gradually you try to drop one of the orders one at a time. On the other hand, when you are dropping, you also keep a check on the accuracy, and you see that at a certain point when your accuracy drops down, you know that the previous number of bytes that you had considered were the appropriate order of your analysis. So likewise, right, your framework is able to automatically detect the order, and therefore the evaluator need not specify that as an input, and that makes the evaluation much more seamless. So we show various kinds of order analysis both for effective countermeasures and detection countermeasures, showing the general applicability of this tool. So this brings me to the last part of the AI for attack component, which is to look at the like the use of machine learning in the context of PUFs, or physically unclonable functions. So PUFs, as I said, are a digital fingerprint, which means that you can use them as devices. Because of the you can use them as device identifiers. So the reason being is that every PUF circuit, if you implement it on different devices, and if you apply the same challenge to these devices, then the responses that you get from them are statistically independent. So this statistical independence of the device helps you to kind of identify the devices and distinguishes the devices between each other. So now the question is, of course, like there are different applications of PUFs, like random number generators, cryptographic keys, identifications, authentications, and in the industry also PUFs are getting more and more popular. At the same time, this also kind of poses different problems on and challenges on security evaluation of PUF, which I still believe remains a widely open topic. So on one hand, you have to kind of do analysis on unpredictability, unclonability, and so on. But I think the most pressing problem of PUF evaluation is in the context of modeling attacks or machine learning attacks. So in machine learning attacks, you try to kind of observe the behavior between the input challenge and the response of the PUF, and use machine learning techniques like SVM, artificial neural networks, and so on, and try to develop a mathematical model of the PUF, or the mathematical approximator of the PUF, which is able to predict the response given an arbitrary challenge. Once it is done, the entire PUF is compromised. So if you look at PUF timeline, you will see that it has been a make and break of PUFs. For example, we started in 2002 probably with the definition of an arbiter PUF, which is probably the first silicon-based results on PUFs, followed by 2003, when people showed how machine learning can be used to attack PUFs. Now they were again, developed to, instances which are called as XOR arbiter PUFs, which tries to basically add non-linearity to the PUF circuit. However, again, using logistic regression, people showed that one can subvert these methods. Again, people try to kind of, develop more advanced attacks like reliability attacks on XOR APUFs, which is able to break 32-bit XOR APUFs. So then again, there are more instances of PUFs like SN PUFs, interposed PUFs, and so many others which people have proposed. But then again, people have also come up with ingenuine techniques to compromise them. So here is a quick illustration of the various types of PUFs. The arbiter PUF, as I mentioned, was one of the most classical PUFs, which is based on like delay-based techniques. So in this case, you take a cascade of various crossbar switches. So you can see here that if you observe one of the crossbar switches, depending upon the value that you set to the input here, it can either get configured as a straight bar or as a crossbar. And therefore, if there are n bits, then there are 2 to the power of n possible paths that an input pulse that you are giving can take to propagate to the output of these two lines. Now, there is this arbiter PUF. Arbiter PUF typically has an arbiter stage, which is realized using a D flip-flop at the output. And now the output Y essentially will be 1 or 0, depending upon whether this pulse reaches the D port of this flop first or the clock port first. So now people have shown, initially people thought that because of the fact that the delay is unpredictable, every device has got a unique delay fingerprint. If I apply the same challenge to 2 devices, the responses will be statistically independent. However, people have shown later on that they are vulnerable to machine learning attacks. So, but first, let us see the various types of PUFs that people have proposed. For example, in order to thwart the machine learning based attacks, the next strategy probably that was very popular are called as XOR arbiter PUFs. So in this case, you take an arbiter PUF and you take not one such instance, but maybe k instances of them, and you XOR them and give the response. So people had shown initially that 6 XORs are quite sufficient to resist against machine learning attacks. However, again, because of the development of various machine learning based techniques, people have shown that even with 11 and 12 XORs, they are vulnerable. And actually, if you use something which is called as the reliability information, then you can even break 32 XOR PUFs. Now, the thing is that if you have more instances of the XOR, then the PUF also becomes unreliable. So this is a continuous kind of contest between resistance against machine learning and also reliability, which the PUF designers need to address. So likewise, there has been proposals of what are called as interposed PUFs, S-PUFs, and SN PUFs, essentially, which are all interesting topologies to make your PUFs more robust and reliable. However, the story largely has been on the make and break of PUFs. So here is an example of a PUF which is called as an interposed PUF, which is of a different nature, and I would like to quickly mention about that. So interposed PUF was originally proposed at CHESS in 2019, and the idea was that you have got 2 layers of PUF, and the first layer essentially produces a response which is used to generate an output bit which goes into one of the input challenges of the next layer and the final layer of the interposed PUF. However, there was a very interesting paper in subsequent CHESS edition in 2020, where this interposed PUF was splitted and shown that one can develop a novel modeling attack against such kind of techniques. So before I go into the next part, I would rather quickly talk about why essentially arbiter PUFs are susceptible to machine learning based attacks and what is the general philosophy of such kind of attacks. So people have, first of all, like as I mentioned, that the output response depends upon the exact delay instance of the top layer and the bottom layer. And the attack technique was initially kind of trying to investigate, the delay parameters in terms of the individual delay, delays of both the straight lines as well as the cross lines of every switch, and try to relate it with the challenge bits. So it turns out by, like an algebraic operation, one can develop a linear model which relates the output response in terms of the challenge vector and the delay parameters. Now, once you prepare a linear model, as you can probably anticipate, it falls prey onto a linear classifiers, and therefore one can apply various techniques like support vector machines and so on, and therefore really can completely break the promises of arbiter PUFs. So people have, as I said, that come up with techniques which are called as XOR arbiter PUFs, which are more resistant against such kind of attack vectors because of the inherent nonlinearity. However, again, there was a very nice paper following this, which showed how reliability information can be utilized to attack against these kind of instances. So when I talk about reliability-based attack, let me first of all mention what is reliability. So when I take a PUF and if I apply the same challenge again and again, maybe L times, then the response should ideally be the same. But because of the noise inherent into the PUFs, there are some small variations. So one can, measure the reliability information by this kind of formulation, which is nothing but taking the absolute value of L by 2, where L is the number of instances you are applying the same challenge, and subtract the sigma of all the responses. The responses are in this case either zeros or ones. So this H gives you a measurement of the reliability, and one can observe that what you would probably expect is all the time that you are giving this challenge, the response remains the same, but it does not turn out, and therefore you get different values of H, which can be used as a measure of the reliability. So now the question is, can you use this information to attack XOR PUFs? So in this very nice paper by Baker in CHESS 2015, one showed how you can perform these attacks. So the idea of this attack is as follows. So if you observe the XOR PUF structure, you will see that if one of this output of the XOR shown here as Y3, so and it is without loss of generality, but if Y3 varies, then you can see that the output also varies, which means there is a correlation of 1 between the reliability of each component arbiter PUF and the final output. And therefore, using this correlation, one can develop a very nice evolutionary based strategy to learn the individual components. So what they do is initially if the target, for example, say the third arbiter PUF in this case, initially come up with some random choices on the weight values and continuously update the weight values to ensure that the reliability of the PUF, that means the final PUF R, and the individual PUF output is essentially quite high. Now, how do you measure the reliability of Y3? So you try to find out based again on the model values, that means on the delay parameters, the difference of the delay between the D line and the clock line of this arbiter PUF. And if this value or this delay difference is smaller than a threshold, then we say that it's an unstable response and it doesn't add to the reliability. But whereas it is more than a threshold, say denoted as epsilon in this case, then it adds to the reliability value. And that way you can measure the reliability of each component PUF, and you try to correlate with the reliability of the overall response, which you can measure by multiple measurements, as I mentioned just in the previous slide. So using this technique, you can really break, like even 32 XOR PUFs, and therefore using this reliability information, it shows that one can really come up with devastating attacks against such kind of PUF instances. So therefore, this opens up the problem, like to develop and like unearth more development. So in this paper, so there was a paper in IndoCrypt where they showed that how you can take different instances of PUFs which are called as S-PUFs. So in particular, they take 12 S-PUFs. So S-PUFs are nothing but arbiter PUFs where the input challenge is carefully designed so that the property which is called as strict avalanche criteria, which means that if I vary one of the inputs of the challenge, then the output probability of flipping should be 0.5. And if you take such 12 instances of S-PUFs and you pair them, and if you perform an ANDing out of them, and then you take these 6 instances and you XOR them, then the idea was that, and this function is typically what is called as a bent function, which has got a very high nonlinearity, and it was anticipated because of the fact that you are breaking the correlation of the reliability of each instance PUF with the output. It should be able to resist such kind of reliability-based machine learning attacks. However, in DAC in 2021, we showed that that can still be subverted by a similar technique. However, the reliability analysis is slightly more sophisticated. In particular, we observed, our main idea was that the reliability of Z1 depends, since it's an AND gate, and you can easily observe that in an AND gate, the output is reliable if both the inputs are 1 and both of them are reliable, or if one of them is 0, then that bit has to be also reliable. If that bit is 0, then it doesn't really matter whether the other bit is reliable or not, because that is not a controlling input. And likewise, right, if the lower bit is 0, then again the reliability of the other bit doesn't matter. So that way you can break it up into 3 mutually exclusive cases, and you can do a more sophisticated reliability analysis and connect it again with this reliability based evolutionary strategy, and again one can perform pretty accurate modeling attacks. So we show that for different instances which were originally kind of advocated in the paper at IndoCrypt, they are vulnerable to accurate modeling attacks which can really learn these PUF instances. So this make and break motivates us to look into whether we can develop CAD frameworks which can help us to kind of measure at the design level. So design level of the PUFs means that when you are at the pre-silicon stage of the PUF, can you perform an analysis to kind of like estimate the PUF complexity? I mean the PUF modeling accuracy complexity. So this kind of takes us and like motivates us to resort into techniques which are called as pack learning. So pack learning is a technique which borrows ideas from machine learning theory and tries to develop a probably approximate correct model of a PUF. So one can kind of observe that a PUF is, if I take a 1-bit PUF, it is inherently a classifier, which means it basically tries to take all the challenges and split it into 2 different hyperplanes. In one of the hyperplanes, the output is 0, and in the other plane, it is 1. So if the machine learning attack is able to kind of understand the hyperplane, then it wins. So in theory, the idea that is often used to develop, models of your what are called as the concept class, which you essentially wish to learn by using a hypothesis class, which is your inference, which is your machine learning model. You try to measure the error, which is essentially denoted as epsilon in this case, and you try to give a bound on this error. And you try to ensure that this analysis should be correct with a sufficient amount of confidence. And this gives us another parameter which is called as delta. So the accuracy of your pack model is often kind of captured by these 2 notions, with these 2 symbols, epsilon and delta, which gives you, an estimate of your accuracy and your confidence. So the idea that is often borrowed is that you try to kind of model such kind of, concept classes by a linear threshold function, or LTF, which essentially is nothing but denoting a hyperplane. So one of the techniques that is adopted to learn the hyperplane is by applying an online method, which is called as an online perceptron algorithm, where you essentially update the weights, and you update the weights when you do not when your prediction is not accurate. So using this, you try to kind of develop a theory which gives you a complexity bound and analysis to show you that if there is a more concept class which is pack learnable, then it implies that your access to the oracle for learning requires polynomial number of access, and the overall time is also polynomial. So using this, researchers have shown that the previous PUF instances like arbiter PUFs, XOR arbiter PUFs are all vulnerable to pack learnability, in one of our recent findings, we also showed that the interposed PUF, which I talked about, is also pack learnable, which means that the pack learning requires polynomial number of accesses to the oracle for doing like the perceptron learning algorithm, or apply the perceptron learning algorithm to learn the LTF, the corresponding LTF or linear threshold function, and it also requires polynomial time. So the question is, can you develop this in a CAD framework? And of course, we know that the advantages of CAD are, of course, kind of well known, that if you can do this, you can do pre-silicon analysis, you essentially can explore your compositions, and therefore, right, it can give us a much better control on the design of PUFs. So in particular, we firmly believe that most of the PUFs that we have seen are prone to pack learnable, but at the same time, the complexity varies. And therefore, that is, I think, a quite interesting point from the practical instance of PUFs. So which means that, well, if I give infinite access to the challenge responses, maybe they are susceptible to model building. But for a realistic attack scenario, maybe in some kind of low-end embedded devices, you can pretty much probably can rule out attacks. Just like like in the context of side channel attacks, right? We essentially often live with some amount of risk, assuming that the attacker will probably not have an access to like an infinite number of power traces, maybe with the same secret key. So therefore, with this motivation, we develop a framework which is called as PUFG, which we published in ICCAD in 2020, which essentially, at the end of the day, it has a front end and a back end. There is a language that we define, and you can describe the various PUF instances in this language framework, and eventually it gives you a sample complexity. So it basically tries to give you various bounds of sample complexities, which tries to kind of gives you sort of a relative ordering of the resistance of these PUF instances versus machine learning. So with this, I would like to kind of hand over the second part to my co-speaker Manar to talk about attacks or the AI for defenses.
So welcome everyone. In the first part of the talk, Professor Debdeep Mukhopadhyay discussed different AI methods to attack various secure computational environments. In this part of the talk, I will discuss different AI methods that can be used as a defense against various threats. I'll start with a deep learning based analysis to detect ransomware programs using hardware monitors. So ransomware is a type of malware that has become a significant threat to multiple business and individuals during the past few years. Ransomware variants target victims and infect an array of devices starting from computers to smartphones. Cybercriminals can attack any consumer or business using these ransomwares, and victims can be from all industries, which can be noted from these news articles. So, what is ransomware? Ransomware are malware from cryptobiology that encrypts file systems on an infected environment. Cybercriminals use ransomwares and force victims to pay ransom amounts for getting the decryption key. A typical snapshot of a victim system after the ransomware attack is shown in the right figure, where the victim is instructed to pay the ransom amount in bitcoins to get the decryption key. One of the most infamous ransomwares in the past few years is WannaCry, which has affected approximately 200,000 businesses across 150 countries. WannaCry has affected an array of devices starting from computers, medical devices like MRI, scanners, blood storage, refrigerators, and many more. It has also affected different major motor manufacturing industries. It was estimated that economic losses due to WannaCry attack could reach up to $4 billion. So there are mainly two types of schemes to detect ransomwares. The static analysis investigates the source codes of programs for the detection. However, unknown new ransomwares can bypass this scheme. On the other hand, behavioral analysis studies the execution behavior of a program for the detection. However, they can lead to high false positives, also false negatives. Hence, newer varieties of ransomwares make a generalized detection mechanism a challenging problem. So what are the challenges in existing countermeasures? Some target specific families of ransomwares. Some require modification in OS kernel, which may not be practical in many real-life environments. Some are susceptible to false positives, and some can be defeated with slow encryption processes. In this tutorial, we'll discuss one dynamic analysis technique. It has already been shown that ransomware leaves threats in the I/O and file system access, and high file system activities correlate with the intuition of ransomwares. These work as motivations of the dynamic analysis technique, which we will discuss next. But before discussing the methodology, let us look into how we can observe system behavior directly from the CPU using hardware performance counters or HPCs. These HPCs are a set of special purpose registers present in most of the modern CPUs. They can be used to count various microarchitectural events from hardware sources related to the execution of a program. The events can be like cache misses, branch instruction, and many more. The Linux-based profiler tool Prof is a simple tool that can be invoked from the command line to collect and analyze these HPC values. HPCs can be in two modes. The counting mode provides HPC values after the complete execution of a program. On the other hand, the sampling mode provides continuous streams of HPC values after an interval of time during a program execution. Now, the question is whether ransomware affects these HPCs. To answer that, we consider a realistic scenario where we monitor the HPCs of a watchdog program and allow the execution of ransomware in the background. We monitor the HPCs in sampling mode and monitor those events which are likely to be affected by ransomware execution. So these are the results that we obtained from the setup, where we can see that the HPC values for WannaCry differ significantly from a typical system behavior. So yes, ransomware do affect HPCs. We published our work on detecting ransomware on host 2019, which is based upon this observation. Now, next question is it enough to observe a single HPC sample point? If we look into this picture, we cannot differentiate between normal and ransomware behaviors by observing a single point. However, if we consider a window of observation, the difference is more apparent. So we consider HPC values as multivariate time series sequences of specific window size. For this analysis, we consider the long short-term memory network, or LSTM. LSTM is a deep learning-based framework which is used efficiently to model sequence data for handling complex dependencies within the sequence. As a first step of the analysis, we use an LSTM-based autoencoder to detect anomalies in terms of HPC behavior. We collect HPC values by sliding the observation window after an interval of 10 milliseconds and model regular system behavior with the autoencoder. The advantage of modeling regular behavior is that we don't need to model the behavior of ransomwares, which makes the method more generalized. Also, we do not need to label the dataset. The intuition behind the anomaly detection approach is that the autoencoder is only shown the normal instances during the training phase and learns to reconstruct them. For any abnormal sequence, the autoencoder will not be able to reconstruct it accurately, leading to high reconstruction errors compared to the benign sequences. These figures show the reconstruction errors for 4 different ransomwares, where we can see the errors are significantly higher than the threshold of normal system behavior. The threshold was selected using the 3 sigma analysis on the normal behavior. Now, can we use reconstruction error as a deciding metric? To answer that question, we analyze different Linux benchmark programs like Spec 2006, Sailstone, Unix, and LMBench. These figures show that the HPC behavior crosses the threshold for normal system behavior in the first autoencoder for some programs in these benchmark suits. This can produce high false positives. So, only reconstruction error cannot be treated as a deciding factor to detect ransomwares. To remove false positives from the detection, we utilize the repeated encryption property of ransomwares. All ransomwares run encryption repeatedly on multiple files. To capture the repetitive pattern, we transform the HPC values in the time domain to the frequency domain using fast Fourier transformation or FFT. These figures show the FFT transformed HPC values for different hardware events. We can see that the amplitude of each frequency bin is constantly higher for the ransomwares compared to the benign programs. As a second step of the analysis, we use another LSTM-based autoencoder to learn the variation in the frequency domain for detecting anomalies. These figures show the reconstruction errors in the second autoencoder for different ransomwares. We can see that the errors are higher than the normal threshold behavior. These figures show the reconstruction error for benchmark programs in the second autoencoder. We can see that the errors are less than the normal threshold behavior. Hence, if the reconstruction errors for a program's HPC behavior in both the autoencoders are constantly higher for some specific time, we conclude that the program is an anomaly. Another difficulty that can arise in detecting ransomware is the existence of disk encryption programs. These programs are very similar in operation to ransomwares. However, the intentions are entirely different. Disk encryptions are benign programs, whereas the ransomwares are malicious programs. Popular disk encryption programs like TrueCrypt and VeraCrypt are detected as anomalies by both the autoencoders as shown in these figures. So as a third and final step of the analysis, we try to identify disk encryption programs. The property that we used is that all the popular disk encryption use the AES XTS mode of operation for the encryption. We template the behavior of a disk encryption process and check whether the suspicious program matches this template or not. We use cumulative correlation over time for the suspicious process for the template matching. If the correlation is high for a successive interval of time, we conclude the process as disk encryption process. In this figure, we use the template of TrueCrypt disk encryption program. We can see that VeraCrypt, being a disk encryption program, shows a high correlation, whereas the ransomwares display low correlation values. But what happens if the ransomware uses disk encryption as a subroutine, like the Mamba ransomware? As a final strategy, we temporarily suspend any suspicious process and wait for a confirmation from the user whether the user has launched a suspected process or not. So this slide presents the overall performance of the detection scheme in terms of detection time of different ransomwares. It also shows the advantage of the method against other related approach, which it can differentiate disk encryption programs from ransomwares, and like they can be employed without changing any kernel module. So next, I will discuss another application where we can use deep learning to counter the threat of rowhammer attacks by analyzing DRAM access patterns. So main memory system or DRAM is a critical component of all computing environments. According to Moore's law, the number of transistors in a dense IC doubles about every 2 years. As a result, DRAM must scale to maintain performance growth and technology benefits. However, the growth in technology increases the possibility of a critical bug in DRAMs, which we will discuss in this part. Before that, let us first look into how a DRAM is organized. Each DRAM is divided into multiple ranks. The ranks are further subdivided into multiple banks. Each bank contains memory cells, which are arranged in rows and columns. And all the rows in the bank are connected through a row buffer. Now, let us discuss how reading and writing are performed in DRAM cells. This figure shows the organization of DRAM cells as rows and columns, which are connected to a row buffer. This figure shows the organization of a typical DRAM cell. Okay, the reading and writing are done through the row buffer. There are 3 steps for reading from or writing into a DRAM cell. First, the row is opened. Reading or writing is performed after opening the row, and then the row is closed. So this opening and closing of rows actually decays the charge in the cell, which needs to be refreshed every 64 milliseconds. So this is the default standard value. Now, as DRAM cells become smaller and smaller, it becomes more vulnerable. If any DRAM row is activated repeatedly, that will lead to loss of charge in the neighboring cells. As a result of losing the charge, a bit value stored in any cell might get flipped. In this figure, we see that the rowhammer process in which the aggressor row is activated repeatedly, and as a result, the cells in the victim row gets flipped. But one thing to be noted is that the row must be activated with high frequency. The frequency needs to be much larger than the automatic refresh rate of 64 milliseconds. The rowhammer bug is a severe real-life reliability and security issues, as a large number of DDR3 and DDR4 DRAMs are practically vulnerable to this bug. An adversary can induce as many as 10 million bit flips in a controlled environment. Using this rowhammer bug, one can gain kernel privilege and take over an otherwise secure system entirely. The rowhammer bug is more damaging as it is easy to induce fault using simple JavaScript. It's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibration opened the door that we're after. There are several countermeasures against the rowhammer bug. However, some require considerable change in hardware and OS kernel modules, which may not be practical in many real-life scenarios. Moreover, the ever-evolving rowhammer bug can bypass existing countermeasures. Hence, an online detection mechanism on existing vulnerable systems seem more reasonable. For a successful rowhammer attack, the DRAM accesses show specific patterns. First of all, the rowhammer bug heavily depends on the device physics. The bit flips are repeatable and they tend to occur at particular locations. An adversary targets specific cells in DRAM with high frequency. Hence, the DRAM access patterns for a successful attack have both spatial and temporal characteristics. They are not entirely random and unpredictable. The DRAM accesses are complex abstractions of virtual to physical address translation and physical address to bank mapping. The virtual to physical address mapping can be obtained by accessing the page map of a system, but actual physical location in DRAM are processor dependent. They can be obtained by reverse engineering the processor's mapping function from the physical address bits. Next, I will discuss two methodologies to detect rowhammer adversaries using deep learning based approach. First, let us look into the profile detection method, which we published in ATS 2019. In the offline phase, we obtain access patterns for both benign and malicious processes. And then we train a convolution neural network, or CNN, to train a classifier that can differentiate between these patterns. In the online phase of the detection, we use LLC misses or last level cache misses as a first level filter. The rowhammer processes which will show significant high LLC misses. In this figure, we can see that DRAM processes show significant high LLC misses in comparison to normal system behavior. The first level filter does not require the CNN for every program, which improves the detection time. We obtain DRAM access patterns for the suspicious processes having high LLC misses and use the previously trained CNN to classify whether the access patterns can induce bit flips or not. In the non-profile based method, we use a CNN based autoencoder to detect rowhammer access patterns in form of anomaly detection. We published this work in SKNS workshop in 2021. In the offline phase, the CNN based autoencoder is trained using benign access patterns that learn to reconstruct the patterns. In the online phase, we again use the LLC based first level filtering. We obtain the DRAM access patterns for the suspicious processes and input them to the autoencoder. For an anomalous sequence, the autoencoder will not be able to reconstruct it accurately, resulting in higher reconstruction errors than the benign access patterns. These figures show the distribution of reconstruction errors for the holdout validation samples. The threshold is computed using the 3 sigma analysis. This figure shows a distribution of reconstruction errors for known and unknown benign programs along with rowhammer programs. We can see that the rowhammer programs show high reconstruction errors compared to the benign programs. These figures show the distribution of reconstruction errors for Linux benchmark programs, which are well below the normal threshold. The advantage of using non-profile method is that we do not require rowhammer programs during the training phase, making it a more generalized approach. Also, we can train autoencoders with an abundance of access patterns from regular benign programs. So, what do we take away from the tutorial? In the first part of the tutorial, we saw 3 different AI-based methodologies which can be used to attack secure computing environments. We saw that one could compromise the security of a cryptographic implementation using power side channel and deep learning. The technique is more efficient than classical statistical approaches. Also, it is more efficient against masking-based countermeasures. Then we saw that the adversary could use deep learning to assess fault attack leakages from a cryptographic implementation. The method is more efficient than the standard t-test-based approach. This has fewer false negatives, and the leakage order can be easily interpreted. Finally, we saw how machine learning could be used to generate efficient models of PUFs. We saw a reliability-based attack using nonlinearity. Also, we saw that the back learning and PUF representation language could enable a better understanding of PUF strengths and weaknesses even before its implementation. In the second part of the tutorial, we saw 2 different AI-based methodologies which can be used against threats on cyber physical systems. We saw that one could build an efficient dynamic defense strategy against ransomware programs using hardware monitors and deep learning. The generalized method does not require any OS kernel modification. Finally, we saw that one could use DRAM access patterns and deep learning to design an efficient defense against rowhammer bug. The processor independent approach is generic and does not require any OS kernel modification. So that's it. Thank you for all your attentions, and please feel free to reach out to us in case of any questions from both the parts. Thank you.
Questions in the chat box.
Yeah.
Are you able to read them?
Yeah, I'm able to see them. And so the first question is on non-profiled side channel attack. So I'm just reading it for everyone. So could you please reiterate how a non-profiled side channel attack is carried out? What do we exactly mean by an S-box there? So a non-profiled side channel attack is essentially a classical side channel attack where you don't have any access to a profiling device. So you have been provided with a target device, you do not know the key. Without doing any like template building or profiling, you essentially have to crack the key, you have to get the key. So usually, right, in classical side channels, they are done by using techniques which are called as correlation power analysis, which is basically computing the correlation and using them to, like distinguish the correct keys from the wrong keys. While in the context of deep learning, we try to do it by, like observing the learning accuracy. So that is the mechanism that we do over here. And the question, like, what do you exactly mean by an S-box? Well, S-box is the full form of S-box is called as substitution box. If you see any good block cipher or any cipher for that matter, it needs to have sufficient amount of nonlinearity. So the S-box is a crucial component in the cipher which gives us nonlinearity, and this is important to ensure that the cipher is resistant against classical attacks or standard cryptanalytic attacks. So that was the answer to the first question. And the second question is I see is like some standard papers to learn about pack learning. Well, pack learning is more, I would say, from the learnability theory. So there are ample amount of resources on machine learning theory from where one can get exposure to pack. But in context to applying pack learning for PUFs, there are some initial works from Fateme Ganji. So I'm just writing down in the chat box. So it is her PhD thesis, and it's from a TU Berlin group. They are the initial proposers of using pack learning for learning PUFs. Subsequently, there are some follow-up works that we also recently did, like the work on that we published at ICCAD that I just now showed.
Right. Many thanks for your responses, Professor Mukhopadhyay. I would like to extend my gratitude to you from the VLSIT Tutorials Committee for delivering this excellent discourse on what is an emerging area and an extremely complex topic. So, Professor Mukhopadhyay, Dr. Alam, and I have specific interests in static RAMs, which are an integral part of the cache subsystem. Mm-hmm. So perhaps someday we can get together and explore similar ideas for caches.
Absolutely.
So again, thanks to both of you, and this session comes to an end.